In this video, we're going to be talking about PDelta static analysis. And for a little bit of background on how PDelta static analysis is implemented within SRAM, it uses a rigorous PDelta approach, where it uses a two-cycle iterative method. First, what happens is the solver performs a linear static analysis. It composes a stress stiffness matrix based on the internal forces from that analysis, and they'll perform a second linear static analysis using that updated stress stiffness matrix. And SRAM can be used to account for both big and little PDelta effects. To help illustrate what this means, let's first take a look at what the big PDelta effect represents. And to illustrate this, I've drawn a simple column here. This is fixed on the base and free on the top. Let's say that we have a lateral load at the tip and an axial load. Well, knowing what we know about structural analysis, we should expect some lateral deformation. Now we can call this axial load here P, and the lateral deformation is going to induce a deflection, which we're going to call big delta. And this is essentially the behavior behind the big PDelta effect. This isn't something that the linear static analysis will be able to consider correctly. It's going to make a lot of simplifying assumptions, which could lead to underestimating the response. But the big PDelta analysis here is going to be considering this offset or this eccentricity from the axial load P, which is going down, to the actual support location. There is a moment arm or a lever arm there that will induce additional deflections and moments and so on. So that's the big PDelta effect. We also have the little PDelta effect, which is similar, different geometry though. So imagine that we have a support at the top and the bottom. We still have our axial load, but we have some sort of lateral force in between the two supports. It's going to be inducing a deflection of little delta, and the same principles still apply. We're going to be getting additional moments and deflections due to this eccentricity from the P, the axial load. Now with the little PDelta effects, when you're accounting for these within SRAM, we always recommend that you add additional nodes along the length of the member so that you don't just have a node at the top and the bottom, but you have nodes in between to accurately account for the little PDelta effects. And we'll see examples of this in the next little while. So let's look at this in action. I've got a model here. It's a two-story frame. And if we just investigate this a little bit more, so if I look at the support conditions, you can see that I have pin supports. And if I look at the releases, you can see that I don't have any releases. So they're rigid connections between each member. I'll take a look at the loads. And we can see that we have two different load cases. We have a factored gravity load case, where we have 1500 kilonewton joint loads at each of the joints above the ground. And we have notional loads here, which is just basically a half percentage of each load in the lateral direction. So we can start by running a linear static analysis. If we run a linear static analysis right now, we'll see the results we get out of this. So we're running a linear static analysis for both load cases, and we also have a load combination combining those two load cases. And you notice here that we're getting a diagnostic message. This isn't something we spent a lot of time looking into, but again, we can refer to this green text here that allows us to access the solver diagnostic messages list. In this particular case, this is indicating here there's an instability about node number 3, which we can look up in just a second, about degree of freedom number 4. And degrees of freedom are numbered 1, 2, 3 for X, Y, and Z translation, and 4, 5, 6 for X, Y, and Z rotation. So this particular issue is with rotation about the x-axis in the model. And just for a little bit of description here, this is the x-axis. So imagine rotating about the x-axis. That's basically the out of plane direction. We don't have any loads in that direction, but because we have pin supports, there's really nothing preventing this model from moving in that direction. So it's just letting us know that the model is not stable in that degree of freedom. Now if I look at the deflections for my load combination, which combines both load cases into one combination, I can see what we're getting here. So I'm just going to look at the load combinations for the gravity and lateral load combination. And I can see in the x direction, I'm getting 11.74 millimeters of displacement. And in terms of moments here, if I just look at maybe this top beam here, I'm just going to right click on the beam. And I can see that I'm getting a maximum of 24.35 kilonewton meters of moment. So we'll just keep those numbers in the back of our heads. Now I'm going to try running a PDelta static analysis. So say run PDelta static analysis. We don't really need to do anything else to run this analysis. We just need to make sure that this option is checked. And we'll click OK to run the analysis. And when we do this, we get a lot more diagnostic messages. When we run into issues during a linear static analysis, it's not oftentimes the case where they become a bigger problem for more advanced analysis types. And that's what's happening here. The issue that was somewhat minor for linear static analysis is growing into more issues with the nonlinear or with the PDelta static analysis. And I can still get the results, but I'm actually wanting to nail this issue and get rid of it. So I'm just going to go to the geometry window, and I'm going to go to Settings, Default Constraints. And what this allows me to do is it allows me to constrain every single joint in my model in a specific degree of freedom. And really, I'm only concerned with in-plane behavior. So that would be basically behaving as a 2D frame, more or less. So I want to allow X translation, Z translation, and Y rotation, but I don't want to allow any other degrees of freedom to be active. So that means I'm going to constrain the Y translation for every joint. I'm going to constrain X rotation, which is actually the problem degree of freedom, and Z rotation. And now I'm going to run this PDelta static analysis again. Press OK. If I drag this over, you can see that we get a clean solution. There's no diagnostic messages. It first ran a linear static analysis, updated the stress stiffness matrix, and then it reran the linear static analysis on that updated matrix. And we can see here that we're getting a clean solution. And now we can look at some of the results again. So for the deflection, we're getting 19.7 millimeters versus 11.7 millimeters of displacement with linear static analysis. And we can see for our moments, we're getting about 34.6 kilonewton meters versus, I think we had 24.3 kilonewton meters for linear static analysis. So that's the major difference, is that we're considering the PDelta effects, the stress state of, or the stress stiffness matrix of the stress state. And so we're getting a more realistic portrayal of what's going on, especially when we have situations where we have lateral loads combined with axial loads that might induce some eccentric loading, eccentric to the actual support location.